Hello everyone, welcome back. In today's video, we are going to discuss a very important topic of Hermitian operators. Now, why is Hermitian operator important in quantum mechanics? You see, all the physical quantities that we deal with, that is position, momentum, energy, etc., the operators associated with those physical quantities are all Hermitian. So essentially, all physical quantities have operators that are Hermitian. Therefore, it is important to understand certain properties associated with Hermitian adjoint as well as properties associated with Hermitian operators, because they automatically translate into those kinds of physical quantities and their corresponding operators. So therefore, Hermitian operator is an important topic in quantum mechanics. So Hermitian operators are operators corresponding to position, momentum, Hamiltonian, angular momentum, etc. So let us spend some time trying to just understand what Hermitian operators are, what is a Hermitian adjoint, and the properties and theorems associated with various Hermitian operators. So what is a Hermitian operator? As I just now said, Hermitian operators usually correspond to operators that are physical quantities. Now, if I make a measurement of a physical quantity in a quantum mechanical system, the answer that I get is a real number. So for example, if I make a measurement of the position and I calculate the average of the position, it has to be a real number. It cannot be a complex number because position is a real value. If I make a measurement of the energy, then the average of the energy should be a real number. It cannot be a complex number, right? You're getting what I'm saying? If I make measurements of physical quantities and their averages, the final answer should be a real number. So that is a property that Hermitian operators satisfy, that if I take a Hermitian operator and I'm going to use A hat and I find out the average of that Hermitian operator, which is essentially, written in this particular manner, then that itself should be a real number, which means if I take the complex conjugate of it, I end up getting the same thing. That is a property of a real number. If I had a complex number, then I would have a minus iota instead. But because it's a real number, it is equal to its complex conjugate. So if I write it in a more detailed fashion, how do you write the expectation value of any operator with respect to some state? So if I have a state psi, I essentially sandwich the operator in the inner product containing psi and psi. In the right hand side also I do the same thing. Sandwich the operator between psi and then you have the complex conjugate. Now what is the effect of the complex conjugate onto the operator that is sandwiched in between? The effect is that you end up getting what is called a dagger, also known as Hermitian adjoint or Hermitian conjugate. So the effect of the complex conjugate on this inner product, which is created by sandwiching the operator between psi ket and psi bra, is that I essentially get a dagger. So what does this lead to? It leads to very simple expression that a is equal to a dagger. And this represents the simple property that is satisfied by Hermitian operators. That is, if you have an operator which is Hermitian, it must satisfy this condition that it is equal to its Hermitian adjoint. And if it doesn't satisfy this condition, then that operator is not a Hermitian operator. At the end of this video, I'll give you some examples of Hermitian operators and non-Hermitian operators. And more importantly, some very common operators that we see in mathematics like derivative, d upon dx. Is that a Hermitian operator? I'm going to prove that to you in the end of this video. But first, let us try to understand this property a dagger. When I say a dagger, what does it mean? It simply means that I am taking what is called a Hermitian adjoint or a Hermitian conjugate. So let us try to understand this property first and then I'll come back to this particular condition. So some of the properties of Hermitian adjoint is if I take a scalar, alright, if I take a scalar which could be a number, a real number or a complex number, and I find out the Hermitian adjoint of the scalar, then that is nothing but the complex conjugate of the number. That's it. Alright, the Hermitian adjoint of a scalar is the complex conjugate of the scalar. Point number 2. If I take a ket or a bra, you know, kets and bras in Dirac notation, they represent the quantum states in quantum mechanics. So in quantum mechanics, all the information of a quantum mechanical system is somehow contained within the quantum state, and the representation of the quantum state in Dirac notation is via ket, and its complex conjugate is basically the bra. So if I take a Hermitian adjoint of a ket, let's suppose, that simply gives us the bra associated with it. And if I take the Hermitian adjoint of a bra, that simply gives us its corresponding ket. As simple as that. If I take an operator, let's suppose A, and I find out the Hermitian adjoint of the operator, and then I take the Hermitian adjoint again, then I end up getting the original operator here. If I operate an operator n number of times, let's suppose, and then I take the Hermitian adjoint, then that is the same thing as taking the Hermitian adjoint and operating it n number of times. Alright. If I take an operator A, multiply it by some scalar small a, and then I take its Hermitian adjoint, that is the same as, because for a scalar, the Hermitian adjoint is a complex conjugate, A star, and multiply to A dagger. So I think you must be getting some idea of what the Hermitian adjoint does. Now in quantum mechanics, especially in the matrix representation, operators are written as matrices, more specifically square matrices. So whenever we are going to be dealing with operators and their representation is a matrix, if I take the Hermitian adjoint of a matrix, what does it do? What does the Hermitian adjoint of a matrix do? By the way, the numbering should be 1, 2, 3, and this is 4, and this is 5. So if you have a matrix, like a square matrix with certain kinds of elements inside, the Hermitian adjoint simply means that first you take the complex conjugate of all these elements and then you take a transpose, as simple as that. This property will help you understand much of the earlier properties. If you have a matrix representation of an operator, the Hermitian adjoint of the matrix representation is the same thing as taking a transpose, which means interchanging the rows and the columns, and taking the complex conjugate of the individual elements. Now, if you have some kind of a outer product, alright, now for inner product, it doesn't really make much of a difference because inner product is a scalar anyways. But if you have something like an outer product that looks like this, let's suppose outer product of psi and phi, and I take the Hermitian adjoint of that, what should that be? I think you can guess this correctly. The ket will become a bra and the bra will become a ket. So you will end up getting phi psi. One last property is that the way we write these kets, sometimes you might see in a textbook that an operator has been written inside the ket representation in this particular manner. Okay, so this is basically a ket representation, but the operator has been written inside the ket representation. In that situation, if I try to take the operator out of it, then the operator will come out as it is, right? But if I do that for the bra, so if an operator is written in this manner within a bra, then if I take the operator out, then I will have to write the Hermitian adjoint here. Alright, now these are just some basic properties that I wanted to mention as to what is the meaning of a Hermitian adjoint, because taking a Hermitian adjoint satisfies all these properties. Now that is not the same thing as Hermitian operators, because Hermitian operators are the ones that satisfies this particular condition. Only reason I've mentioned these properties is because there is a Hermitian adjoint here, and I wanted you to understand what taking a Hermitian adjoint means for scalars, for kets and bras, for matrices, and in general, when you look at the notation of quantum mechanical formalism in a textbook, you will probably see some of these properties being reflected here and there. So it's better that you write all of these down and become familiar to the properties of what it means when you take a Hermitian adjoint. Now coming back to our original discussion of Hermitian operators. So Hermitian operators are those operators that satisfy this particular condition. This particular condition has come from what? Expectation. I already told you at the very beginning. This condition is coming from the fact that we expect the measurements of different physical quantities to be a real number. Whenever you have physical quantities like position momentum, Hamiltonian, angular momentum, spin angular momentum, the measurement of those physical quantities must lead to a real number. Therefore, all the operators associated with these physical quantities must be a Hermitian operator. Their expectation values must be real, and therefore the operators associated with the physical quantities must satisfy this condition that the A dagger is equal to A. That means the adjoint of the operator must be equal to the operator itself. So this is basically known as self-adjoint. So let me make some space here of Hermitian operator leading to self-adjoint. So let me do some numbering also. So I'm going to call it self-adjoint. Now, the moment I say self-adjoint, there are some properties that arise from there, and I want to prove that to you. It's a little bit of a theoretical discussion, but trust me, the things that I'm going to mention here are going to be very helpful for you when you are studying the formalism of quantum mechanics. The first is that the eigenvalues associated with Hermitian operators are real. Okay. Now, how can I prove that? Again, I'm going to take the expectation value method, which is essentially this, that if A is equal to A dagger, and I take the expectation value here, that means A sandwich between psi and psi is equal to A dagger sandwich between psi and psi. Now we know that, we don't know, I'm just assuming that it is obvious that if I take the operator A and it acts on the state psi, there has to be some eigenvalue as long as psi is an eigenstate. So we are assuming the psi here, the kets are eigenstates. Then let's suppose the eigenvalue is lambda, okay? So we end up getting lambda psi. This is a side note, okay? I'm just writing it separately. And if A dagger, if I take the Hermitian adjoint of this whole expression, then A dagger is going to act on psi bra. And if I take the Hermitian adjoint of the whole expression, this simply becomes lambda complex conjugate, because lambda is a scalar, right? And you have the bra here, psi. So if I implement these two expressions here, so for example, I implement the first expression in the left hand side and the second expression in the right hand side, what will I get? So if I implement the first expression here, this simply ends up becoming, I get the lambda scalar out, psi, psi, right? And then if I implement the second expression here, A dagger acting on psi bra, I end up getting lambda star, psi, psi. So what does this lead to? This leads to lambda minus lambda star psi, psi inner product, which is equal to 0. What does it mean? We know that the inner product of an eigenstate with itself is usually 1 as long as they are normalized. So that means this is not equal to 0. If you take the inner product of a state with itself, it is not equal to 0. That means the only remaining possibility is lambda is equal to lambda star, which means what? It means that because lambda is the eigenvalue of A, right? Lambda is the eigenvalue of A, you can see it here. The eigenvalues of self-adjoint operators or Hermitian operators are always real. That's it. Eigenvalues of Hermitian operators are real. So this is one very important property. Now for the next property, which is also kind of important, you must be familiar with the fact that in a given quantum mechanical systems, there can be multiple eigenvectors, right? There can be multiple eigenstates. Now what the next property says is that if you have a Hermitian operator which has two distinct eigenvalues corresponding to two distinct eigenvectors, then those eigenvectors are going to be orthogonal. I will give you an example of this also, but let me first prove this. So for example, if you have two distinct eigenvectors, let's suppose psi and phi corresponding to operator A, let's suppose it has an eigenvalue lambda and phi has an eigenvalue gamma. Then if I take the inner product with respect to psi and phi by sandwiching the operator within it, so if I have psi A phi, because A is equal to A dagger, I can also write psi A dagger phi. Now here what is going to happen? A is going to act on phi and I am going to get gamma, okay? And then you have psi phi inner product. In the right hand side, what is going to happen is that A dagger is going to act on bra of psi, right? If A acts on psi, the eigenvalue is lambda. But if I take the Hermitian adjoint of this whole equation, then A dagger would act on psi bra, and here instead of lambda, we will get lambda star. So complex conjugate of lambda. So here I should get lambda star, okay? And this should give me psi inner product with phi. Now if I simplify this expression, what do I get? I end up getting gamma minus lambda star, and here I have inner product of psi and phi is equal to 0. But if gamma and lambda are not equal, anyways I have already proved that the eigenvalues of Hermitian operators are all real. That means lambda star is equal to lambda, because lambda is a eigenvalue of a Hermitian operator, so it's a real number. So gamma minus lambda, if they are gamma and lambda are not equal, if gamma is not equal to lambda, then it is obvious that psi inner product with phi is equal to 0. What does it mean? You must have seen this kind of an expression before. If there are two eigenkets or eigenfunctions or quantum states and their inner product is equal to 0, it means that they are orthogonal to one another. So if there are two eigenvectors corresponding to the same Hermitian operator, then they are orthogonal if the eigenvalues are not equal. That means if it is not a degenerate state. So this property is written as eigenvectors corresponding to distinct eigenvalues are orthogonal. Eigenvectors corresponding to distinct eigenvalues of the same operator, of the same Hermitian operator, are always orthogonal. Now what could be an example of this? A very simple example of this is if I take the infinite potential well. So you guys are aware of the infinite potential well, that the infinite potential well has infinite eigenvectors and infinite eigenvalues. So the Hermitian operator is the Hamiltonian, and the Hamiltonian eigenvalues are the energy levels E1, E2, E3, and the eigenvectors are, let's suppose phi 1, phi 2, phi 3, right? So here we have the example of an infinite well where the Hamiltonian acting on, let's suppose, phi1 will give us E1, right? And the Hamiltonian acting on, let's suppose, phi2 will give us E2, right? E1 and E2 are not equal, so phi1 and phi2 are orthogonal. In fact, for an infinite potential well, all the infinite eigenvectors are orthogonal to one another, which leads to the third property that all the eigenvectors corresponding to a quantum mechanical system form a basis set for that quantum mechanical system. To show that, let me rub this portion of the board. If you want to take note, you can just pause the video or take a screenshot of this. Let me just rub this portion to clear up some space. Eigenvectors of a Hermitian operator represent a complete set of orthonormal bases. You can see this from this particular example, that if I take the infinite potential well and I look at the eigenvectors of the Hamiltonian for that infinite potential well, then all these eigenvectors are essentially orthonormal to each other. That means if I take the inner product of eigenvector with itself, I'll get 1. If I take the eigenvector inner product with something else, some other eigenvector, I'll get 0. So all these eigenvectors of the infinite potential well corresponding to the Hamiltonian operator represent a complete basis for this particular system. That means any kind of a state, any kind of a general mixed state of this system can be represented as a linear combination of these eigenvectors of the Hamiltonian. In fact, this is a general statement that if you have a Hermitian operator for a quantum mechanical system, all the eigenvectors for that particular system will represent an orthonormal basis. That means any general state can be represented as a linear combination of the basis, which are nothing but the eigenvectors of the Hermitian operator for that system. I hope that it has not become too complicated and too mathematical for you. Trust me, I'm trying to keep it as non-mathematical as possible, but because we are studying a subject of quantum mechanics, which in itself is a hugely mathematical subject more or less, because we are dealing with so many different kinds of mathematical operators, we have to study their properties, we are dealing with quantum states, we have to study their properties. 90% of our job is essentially sort of navigating the mathematical formalism of quantum mechanics. Therefore, these properties that I am mentioning here, especially that is corresponding to Hermitian operators, are actually going to be useful for you if you do a detailed study of advanced quantum mechanics. So this brings me to the last property of Hermitian operators. It is that if you have two Hermitian operators, A and B, let's suppose, and A has no degeneracy. Degeneracy means that none of the eigenvalues are equal. If you have two Hermitian operators A and B and they commute, that means AB is equal to BA, then the eigenvectors of A are also eigenvectors of B. So let me show it to you. So if you have an operator A, all right, and if you have another operator B, and A is such that when A acts on psi, you end up getting lambda psi, and B is also operator such that A and B commute. That means AB is equal to BA. Now usually, whether two operators commute or not, that depends upon the detailed nature of the operators. Usually in quantum mechanics, most operators do not commute. Now, sometimes if they do commute, that means if I can write A acting on B acting on a state the same as B acting on A acting on a state, now what can I do about it? So what can I do is, I can write A B acting on a ket is the same as B A acting on a ket. But you know that A acting on psi is nothing but lambda psi. So if I write it in this manner, A acting on B acting on psi is equal to, what do I get? Lambda psi. Lambda is a scalar, I can take it out. Lambda, then I am left with B acting on psi. Now look at this equation. A acting on B acting on psi, or A operating on B operating on psi, and lambda times B operating on psi. What does it look like? This looks like an eigenvalue equation, right? If I think of B psi ket as some state, because that is what operators do, B acting on psi will lead to some state, let's suppose psi star, whatever, or psi dash. So this is a psi dash, this is psi dash. So A psi dash is equal to lambda psi dash. So this is an operator eigenvalue equation. That means B psi ket is an eigenvector of A. It's interesting, right? B psi ket is an eigenvector of A according to this equation. Now if B psi ket is an eigenvector of A, we know that all the eigenvectors are kind of unique, because from here we know that if a particular operator has multiple eigenvectors from this particular property and they do not share the same eigenvalue, then all those eigenvectors are orthogonal. That means they are unique, they are independent of each other. So if all the B psi kets are unique, that means psi is also going to be unique. And as a result, psi, which is originally an eigenvector of A, must also be an eigenvector of B. Alright, so it simply means that if two Hermitian operators A and B commute, this is important, then the basis of one vector is the basis of the other vector. And A has no eigenvalue, no degeneracy. Okay, A has no degeneracy. Then all the eigenvectors of A, all the eigenvectors of A are also eigenvectors of B. That means both A and B share the same basis. Same basis. So all these properties that I have mentioned of Hermitian operators, that Hermitian operators have real eigenvalues, that if a Hermitian operator has multiple eigenvectors corresponding to different eigenvalues, then those eigenvectors are going to be orthogonal, that the eigenvectors of a Hermitian operator represent a complete mutually orthonormal basis set, that if there are two Hermitian operators A and B which commute, then they share the same basis or they share the same eigenvectors. They are important because they all are effectively the properties of the operators corresponding to the physical quantities that we are going to be dealing with most of our time, whether it is position, momentum, Hamiltonian, angular momentum, spin angular momentum. All the physical operators, all the operators corresponding to physical quantities will correspond to these properties. So I hope that you have taken a note of all these properties. You have taken out a notebook and written all of them down. You can take a snapshot if you want. You can pause the video. I'm going to move ahead to justify this video with the thumbnail. If you looked at my thumbnail, I simply asked you a question: is d by dx a Hermitian operator? You see, some of the common operators are derivatives, right? We deal with derivatives all the time. D upon dx, it's a derivative with respect to x. Is d upon dx a Hermitian operator? Is d upon dx, does it correspond to a physical quantity? That's a good question, don't you think? So let me rub the board and let us come back to analyzing the operator d upon dx. Alright, very important question. Is d upon dx, the derivative that we are so fond of, that we regularly use in our calculations in quantum mechanics, is that a Hermitian operator? What do you think? Before we reach the answer, you can write your answers in the comment section and you can cross-check if you have achieved the correct answer. D upon dx, is it a Hermitian operator? Let's check. Let us say that the operator A is d upon dx. Alright, now what am I interested in right now? I am interested in figuring out the expectation value of A, let's suppose, okay, which is written as, with respect to some eigenstate psi, d upon dx sandwich between psi and psi ket. Now, d upon dx is a derivative with respect to x, with respect to position representation essentially. So whenever we do calculations with respect to position representation, we write the eigenstates as an eigenfunction, as a mathematical function. And what we do is we sandwich the operator within an integral between psi star and psi. So that is how I am going to write it, because that is how it's going to make sense. So if I write psi ket as a psi x, then essentially it means that I have for psi bra, let's suppose I'm writing it in position representation as psi x, which is a mathematical function of x, but because this is a bra, it is a complex conjugate. The operator comes here and the operator acts on everything that follows. So this is psi, so it acts on psi x, right? So this is what you have. Integration with respect to dx between minus infinity to plus infinity. That's it. This is the expectation value of d upon dx operator with respect to some eigenstate psi x. If I simplify this integral, what is going to happen? This is a mathematical function. This is also a mathematical function. I can separate the product of functions within an integral sign by taking this out. So I can write psi star. And then we are left with integration of d psi upon dx, right? Dx. What is this? Integration of d psi upon dx integrated with respect to dx is just nothing but integration of d psi, which is nothing but psi. Okay. So if this is psi, then I'm going to write psi here, x, but it is between the limits of minus infinity to plus infinity. All right. Minus integration from minus infinity to plus infinity. This function I'm going to take derivative d psi star upon dx, and here of course integration of d psi upon dx with respect to dx is going to give me psi x, again dx. Now here we have the eigenfunction in the limits of plus minus infinity. You must remember from our previous lectures that the wave function of any kind of a quantum mechanical system at infinity goes to 0. That is the only way for us to normalize it properly. So therefore, this expression is 0. So if this is 0, the entire expression becomes 0. We are left with what? This expression. Now if you look at this particular expression, just look at it carefully. What is this? This is nothing but the inner product of d psi upon dx in the bra with respect to psi. Now if you remember when I was talking about the properties of the Hermitian adjoint, what happens when an operator is acting on the bra in an inner product? The moment we take it out, what happens? We end up getting the Hermitian adjoint. So d upon dx, Hermitian adjoint psi. Now, one thing I forgot to write is the minus sign here. There is a minus sign here, right? There is a minus sign, and therefore there is also a minus sign here. Okay. So if I compare this with this, does it look like the d by dx Hermitian adjoint is equal to d by dx? No, there is a minus sign here. You see what's happening? So the Hermitian adjoint of d by dx is equal to minus d by dx. So finally, we have obtained that d by dx Hermitian adjoint is equal to minus d by dx. So does this satisfy the property of Hermitian operators? Come on, come on. Does this satisfy the property of Hermitian operators? No, it doesn't, because Hermitian operators are self-adjoint. The Hermitian adjoint of an operator must be equal to the operator itself. Only then it's a Hermitian operator. This is not. This d by dx of Hermitian adjoint is not equal to d by dx. In fact, there's a minus sign here. This is called a skew Hermitian operator. I'm going to come to that in a moment. This is a anti or skew Hermitian operator. So that means what? That means our favorite operator, such a common, popular, famous operator in the context of the mathematics of quantum mechanics, d by dx, cannot be used for physical quantities. So you will never find a physical quantity like energy, position, momentum, whatever, which is associated with some operator d by dx. Now, however, we can combine d by dx with other things to make it a Hermitian operator. For example, if I write something like iota d upon dx. Now, this is a different operator because now I have multiplied the scalar iota to d by dx. What if I take the Hermitian adjoint of iota d by dx? You know that iota is a scalar. You take the complex conjugate, d by dx, you take the Hermitian adjoint. Iota scalar is minus iota, so minus iota. D by dx Hermitian adjoint is minus d upon dx. Both combined is equal to iota d upon dx. There you have it. Iota d by dx is a Hermitian operator. Now tell me something. Have you seen iota d by dx used as an operator for some physical quantity? Come on, make a guess. Yes, you have. You must remember the momentum operator. You remember the momentum operator, right? What is the momentum operator? If you remember the momentum operator, P is nothing but minus iota h cross d upon or del upon del x. H cross is a constant, so you don't have to worry about it. Minus iota h cross del upon del x. So the momentum is a Hermitian operator because momentum is a physical quantity. That's the whole definition from the starting point of what Hermitian operators are. So the momentum is a Hermitian operator where we have iota d upon dx. But just d upon dx itself is not Hermitian. Isn't that interesting? No, that's kind of fascinating, right? Because you deal with d upon dx all the time, but it turns out it's not a Hermitian operator. It cannot be used for a physical quantity. Now, taking this discussion forward, I'm going to show you some more interesting things. Now, let me talk about d2 upon dx2. What about this? Do you think this is a Hermitian operator? Come on, quick. You can pause the video, write in the comments what do you think d2 upon dx2 is. Is it a Hermitian operator? Yes or no? Pause the video, write it in the comment section, and then you can then forward the video and check the answer for yourself. Is this a Hermitian operator? For this to be a Hermitian operator, we have to check its Hermitian adjoint. Let me check. So d2 upon dx2 can be written as d upon dx, Hermitian adjoint. Now, we know the properties of Hermitian adjoint. I talked about it at the beginning of the lecture. This can be written as d upon dx, Hermitian adjoint, d upon dx, Hermitian adjoint, which comes out to be what? Hermitian adjoint of d upon dx is minus d upon dx. This in itself is a very important expression. So better you write it down separately as a formula. So This is minus d upon dx. This is minus d upon dx. Combined, we end up getting minus minus becomes plus d2 upon dx2. There you have it. d2 upon dx2 is a Hermitian operator. Now, can you tell me some physical quantity that contains d2 upon dx2? Very easy, very easy. Come on. Hamiltonian. The Hamiltonian operator contains d2 upon dx2. So the Hamiltonian is minus h cross square upon 2m. Don't worry about it. This is just a constant. And you have d2 upon dx2 plus some real potential Vx. So the Hamiltonian contains d2 upon dx2. Now, from here, you must have got some idea about different kinds of operators. So, let us do a quick test. Do you think that, no, you already know by now, d upon dx, is it a Hermitian operator? It's not. But iota d upon dx is a Hermitian operator. Yes? What about d2 upon dx2? Is it a Hermitian operator? Yes. Now, let me ask you a question. What about d cube upon dx cube? Is it a Hermitian operator? No. You can do a similar calculation and check for yourself. But if I introduce an iota here, then it becomes a Hermitian operator. What about d to the power 4 upon dx to the power 4? Is that a Hermitian operator? Yes. Do you see how this is going? Whenever you have these odd derivatives, power odd, you multiply with an iota. Otherwise, for the even ones, you don't have to do anything. They are all Hermitian operators. So based on this, you can take any theoretical power of the derivative and check whether it is Hermitian or not. Now, before we wrap up this video, I want to mention a few comments about skew Hermitian because this is also important. So let us just take a few moments trying to understand the skew Hermitian. Or anti-Hermitian operator. Alright, so what is the skew Hermitian operator? Skew Hermitian operator is when the Hermitian adjoint of the operator is equal to the negative of the operator. That means if I have an operator A and I take its Hermitian adjoint, it is simply is equal to minus A. That is the condition for a skew Hermitian operator. Now, if I take the expectation value on both sides, I end up getting psi A dagger psi is equal to minus psi A psi. So what is going to happen here? Of course, A dagger is going to act on the bra, and let's suppose the eigenvalue corresponding to this is lambda. So I end up getting lambda complex, lambda star, and we have psi psi. And here A is going to act on psi. I am going to have minus lambda psi psi inner product, which means what? It means lambda star plus lambda is inner product of psi and psi is equal to 0, which means because this is equal to 1, I finally have lambda star is equal to minus lambda. When is this possible? If I have a scalar, if I have some number and I take its complex conjugate, it is equal to its negative. When is that possible? Come on. It is possible if it is purely imaginary. So therefore, eigenvalues eigenvalues of skew Hermitian operators are purely imaginary. So I hope you have understood this particular lecture. If you are a student of India and you are planning for various examinations, competitive examinations in India like Physics IIT, JAM, CSI NET, etc., we regularly launch live as well as recorded courses for various competitive examinations. You can check out all those courses at elevateclasses.in. If you want to join, you can join with me and start your preparation. So I hope you have understood everything in this particular lecture, and the topic of Hermitian operator now is much more clearer to you. In the coming lectures, I'm going to talk about some more operators, not necessarily Hermitian, but some more mathematical operators which are very relevant in the context of quantum mechanics. I will see you next time. This is For the Love of Physics. I am Divya Jyoti Das. Thank you so much. Take care. Bye-bye.